So if we start with the first point, vapor pressure estimation. So if we recall chapter 2, this is the chapter that we start talking about the phase equilibrium. So in this chapter, we will, as we said, we will use some methods. This method we will use to predict this like phase equilibrium or vapor pressure. Vapor pressure, this is the pressure at which we have phase transition or phase happens for pure substances. And if you remember from chapter 2, we defined two things. We defined saturation temperature, and we said this is the temperature at which pure substance will change its phase at a given pressure. And we have something called saturation pressure or vapor pressure. This is the pressure at which substance will change its phase at a given temperature. And this saturation pressure, saturation temperature are related, and they are like directly proportional with each other. And the common example we said for this one is water. So we said if we have water at atmospheric pressure, then phase change from liquid to vapor or vapor to liquid will occur at 100 degrees Celsius. So 1 atmosphere, this is the vapor pressure for this temperature. 1 degree Celsius, this is the saturation temperature for this pressure. So these are like connected together. For the phase change for water to occur, so the pressure is 1 atmosphere, then the temperature must be 100 degrees Celsius. Any other temperature at 1 atmosphere, you will not have phase change from liquid to vapor exist. But if you will have 2 atmosphere, then the saturation temperature will increase. Not be 100 degrees Celsius, can be 120 or 130, for example. Okay, make sense? Okay. So the question is how we can calculate this, like pressure, this vapor pressure. If I tell you that I have water, for example, at 130 degrees Celsius, and I need phase change to occur at this temperature. So what is the corresponding pressure at this temperature at which phase change will occur? Okay, it can be 1.3 atmosphere, 1.5 atmosphere. So what is the value of this vapor pressure? So there are several methods that we can use to calculate this vapor pressure. Okay, and we have like 3 main equations we can use. We will focus on this one, even we will have example on this one. But we need to describe quickly these 2 equations. What are the differences between them? So the first equation was Clausius-Clapeyron equation. Then scientists developed the shortcut method, and then they end up with the Antoine equation. So this is the historical arrangement of how they appear. So the first one, Clausius-Clapeyron equation, this was a special case of Clapeyron equation. So we have an equation, it's called the Clapeyron equation. We developed this equation by Clausius, and this is why it's called or named after their both names, Clausius and the Clapeyron equation. There is a long derivation in the textbook, but let's focus on the final form in the equation. So the final form in the equation, it tells you if you need to calculate or estimate vapor pressure of pure substance, you can use directly this equation. It says ln saturation pressure 2 divided by saturation pressure 1 equal negative latent heat of vaporization of this pure substance divided by the ideal gas constant divided by 1 over T2 minus 1 over T1. And if you just see the nomenclature, P2 sat, T2 sat, these are the saturation temperature, saturation pressure that are related together. P1 sat, T1, these are the saturation temperature, saturation pressure that are connected together. If you look to this equation, and if I tell you, for example, I have, let's put temperature, if you have water, for example, and for water, I need to find saturation pressure at 150 degrees Celsius. So let's say this is the condition. I need to find saturation pressure at 150. Since we are talking about water, then we know that one given information about water that at 100 degrees Celsius, the saturation pressure equal 1 atmosphere. We know this data for water, right? Then we can use this one as T1. And we can use this 1 atmosphere as P1 sat. And we can assume this 150 in the equation, this will be T2. And then the whole thing that we need to find T2 sat in the equation. So we'll substitute in the equation P1 sat, this is known, 1 atmosphere. P2 set, this is the unknown that I need to find, or this is the ideal gas constant. Delta H vaporization of water, I can get it from the appendix. This is very easily. T1, this is the 100 degrees Celsius. T2, this is the 150, the temperature at which I need to find the saturation pressure. Substitute in the equation, calculate the saturation pressure at 150, and that's it. Okay. But one of the things that we have for this equation is based on some assumptions. The first assumption is the latent heat of vaporization is constant. This is the first assumption for using this equation. So if you have substance and latent heat of vaporization is not constant, this equation will not be valid. So when this assumption can be valid, this assumption can be valid if T1 and T2 are close to each other and both of them is not near the critical point. Okay. So this is the case that makes this assumption is valid, and if this assumption is valid, then we can use this equation. Okay, so T1 and T2 should be close to each other, and both of them are not clear to the critical temperature of this substance. So this is the first assumption. Second assumption is the molar volume of liquid is neglected compared to molar volume of vapor for the same substance. Here we are calculating vapor pressure at which the liquid will be converted to vapor. So we have volume of vapor, volume of liquid. These are the two phases existing together. So whatever the molar volume of vapor we have, this will be very large compared to the molar volume of liquid, and we can compare the molar volume of liquid. And the molar volume of vapor, this one is modeled by ideal gas, or the substance you have can be described as an ideal gas. And these two assumptions are valid if you have low pressure. So again, we have some assumptions for this equation. In order to use this equation, then latent heat of vaporization should be constant, and this happens if T1 and T2 are close to each other and far away from the critical temperature. If the pressure, this vapor pressure is low, because if the vapor pressure is low, then you can assume you have ideal gas behavior. You can assume that the molar volume of liquid is neglected compared to the molar volume of vapor. And only if you have these conditions like achieved, then you can use this equation. But even if you have all of these conditions achieved, there is one important point in order to use this equation. You need to know existing information. You need to know T1 and P1 set. This must be known. Okay, I can tell you calculate vapor pressure at 150 without giving you this information. If this information is not given, if this information is not known, for example, and even if these assumptions are valid, these assumptions are fulfilled, but you are missing this data, then either you can't use this equation. So the problem is for this equation, Clausius-Clapeyron equation, this one, valid only at low pressure. We have some limitation on the T1 and T2. In order to find P set at T2, you must have one temperature, one saturation temperature, one saturation pressure. If you are missing this information, you can't use this equation. Clear? So this is why we need to develop other equations, and scientists, they developed another one. It's called the shortcut method. And this shortcut method, it have this form. And again, the derivation of the equation in the textbook, if you need to know how this equation came from. So this one tells you that logarithmic mean of reduced saturation pressure. Do you remember reduced something? Reduced the property is the property divided by the critical value of this property. So if you recall that we have reduced temperature, this is temperature divided by critical temperature. We have reduced the pressure, this is pressure divided by critical pressure. Reduced saturation pressure, this is saturation pressure divided by critical pressure. So logarithmic mean of reduced saturation pressure, this is 7/3 omega plus 1. Omega, this is the eccentric factor. If you remember it from chapter 3 or 4, its value is from 0 to 1. It's 1 for noble gases or symmetric gases, 0 for completely asymmetric gases. Okay, times 1 minus 1/T reduced. So again, omega, we have equation to calculate this omega, and even we have appendix to calculate this one. So the best thing to find this omega, we have appendix in the textbook that have the value of the eccentric factor for each substance. If you don't have this value in the appendix, then you can use this equation. Critical pressure is P over Pc, critical temperature, or reduced temperature, reduced saturation temperature. Okay. So this is the equation, direct substitution. One advantage that is clearly appearing in this equation that you don't need T1 or P1 sat in order to calculate the vapor pressure. Just give me the temperature at which you need to find vapor pressure. I will substitute directly with this temperature here, and I will find the vapor pressure. There is no need to like have T1 or P1 sat and then assume T2 and find P2 sat. This is not like existing in this equation. So this was one of the advantage of this equation over Clausius-Clapeyron equation. But the issue for this one, it's valid at high pressure, okay, and also valid at ideal gas conditions. Okay. One of the limitations of this equation that it can be used if the T reduced like lies within this range. Outside this range, the accuracy of this equation, like you have some doubts about the accuracy of this one. So again, so far we have two equations. Clausius-Clapeyron equation, valid at low pressure. And this equation have some assumptions. And in this equation, we need like given point, given saturation temperature, given saturation pressure in order to use it. Shortcut method, just there is no need for any given like saturation pressure or saturation temperature. Just directly substitute in the equation. But the issue in this one, it's valid at high pressure and it's valid within this range of reduced temperature. So each one of them have some limitations. And if we compare the predictions of each one of them with existing data, so let's see this figure, for example. This is like some data we obtained at low pressure. This like black squares, these are the actual vapor pressure. This line here, this is the prediction of Clausius-Clapeyron equation, and this line here, this is the prediction of shortcut method. So at low pressure, Clausius-Clapeyron equation, this one gives you the like the best fit for the data. If you have moderate pressure, like not very low, not very high, then both equations can give you like accurate results. At high pressure, as you can see, the shortcut methods directly lies on the actual data, and this is the prediction of the Clausius-Clapeyron method. So each one of them have some limitations in order to use. Okay. Then scientists, they like start to improve their equations and they end up with the Antoine equation, and this is the most recent one, and this is the one that we will use. Even we have an example today we will solve for this one. Antoine equation, this one, it tells you that logarithmic mean of saturation pressure, directly saturation pressure, not reduced saturation pressure. Okay, logarithmic mean of saturation pressure is A minus P over T plus C. And again, just one temperature. There is no need to have any given saturation temperature or saturation pressure. Whatever temperature you have, substitute in this equation, calculate saturation pressure that is corresponding to this temperature. But in order to use this one, we need to find what is the value of A, what is the value of B, what is the value of C. And these are parameters. These parameters, directly you can find them in Appendix D. So these are constants. A, B, C are constants, even not equations. Direct constants, you get this constants from the appendix and then substitute them directly in this equation. But one of the things that we like to consider for using this equation, these constants are listed within a recommended temperature range over which they can apply. And now let's see what this means. If we see Appendix E, so this is the picture of Appendix E for Antoine equation. This appendix tells you this is the equation that we can use in order to find saturation pressure. The first thing to observe in this one is he's telling you here, this saturation pressure is expressed in millimeter mercury. And the temperature that we are using here is expressed in degrees Celsius. This seems not consistent in terms of dimensional homogeneity. So in all of the previous like equations, we are talking about dimensional homogeneity. We should use a single like system of units. All the equations should be in SI system. All the equations should be in CGS system. But here in this equation, this assumption fails. In order to use this equation, you should stick with these units. Any temperature here, it should be substituted with degrees Celsius. Any pressure should be in millimeter mercury, not atmosphere, not bar, not Pascal, Okay, not anything that of the common the units you are using, only millimeter mercury. Okay, and why this happened here? We have one type of the equations. This equation is called empirical equations. Empirical equations means people did a lot of experiments, and then they collected all of these experimental observations or experimental data, and they put it in statistical software, and they end up with an equation that best fits this like experimental result they have. This empirical equation, in order to find the best one, they don't focus on, or there is no rule that for them to or obligation to stick with a single set of units. They can give you any equation with any set of units. They can make combination of units. This is fine for this kind of equations. Okay, but if you will use this equation, you must use the equation that they have developed or they used in order to develop this equation. So this is why here we will use the temperature in degrees Celsius, and we will use this saturation pressure in millimeter mercury. And this is the only equation we have in this course that violates the rule of dimensional homogeneity. Okay? So now we have this one, and then we have this table. The first column is name of the substance. Second column give you the structure, and then the value of A, the value of B, value of C. ABC not multiplies by like 10 to the power 3, 10 to the power 5. So this is not like heat capacity equation or heat capacity appendix. Directly take these numbers as A value, B value, C value. So if I tell you I have like acetone, for example, so I have acetone. So this will be the value of A for acetone. This will be the value of B, and this will be the value of C, and these are the value of ABC if acetone is liquid. Okay. But if I have like benzene, for example, here for benzene you will see that we have two rows. So the value of A can be this number 9 or can be 6. The value of B can be this number or can be this number. The value of C can be this number or this number. So which row you will use? So based on the temperature you have in the equation. If the temperature, given temperature lies within this range, then this will be the row that we will use. If the given temperature lies within this range, so this will be the row or the value of A, B, and C that you will use. So this is the statement that we said the value of A and B and C are valid within a certain range of temperature. Okay, so if you have any substance have two rows or have three rows for A, B, C for this substance, then check the temperature range. What is the given temperature? So for the given temperature, find it here. If it lies within this range, so go directly and use A, B, C. If it's the temperature between 8 and 103 degrees Celsius, then this will be the value of A and B and C that you will use in the equation.